Hello everyone, welcome to angular SHM and total energy for simple harmonic motion. Now for angular SHM, so this is the SHM which happens in an angle where the body does not get displaced but only from their mean position. So let's say a circular disc is hanging from a rigid support, and here in that axis it just tilts like this. So here the body itself isn't swinging here and there, but its body is oscillating like this to and fro, creating some angle like this. So that would mean from here it would create equal tilting of angle theta, let's say. So here there will be a restoring force in the opposite direction. And here, according to Hooke's law, we know that the restoring force is directly proportional to displacement. Similarly, we have the restoring torque is directly proportional to the angular displacement. So tau is equals to minus c theta, where c is the torsional constant and negative signs means, well, it acts in the opposite direction to that of the displacement produced. So tau we know is I alpha, because we have force equals to ma and tau equals to I alpha. Analogies we have discussed in rotational dynamics, and I will prove for this in a future video. So here I alpha equals to minus c theta and alpha equals to minus c by I theta. Minus c by I theta. Well, here c is constant and moment of inertia of body is also constant. So alpha is directly proportional to theta, proving the angular SHM. Now from here we know that angular acceleration is equals to minus omega square theta, and comparing with this we get omega equals to root c by I. Therefore time period equals to 2 pi by omega, which is that, so we get I by c. So now for total energy. Now here total energy of a body in simple harmonic motion is basically the sum of its kinetic energy and potential energy. Now let's start with the kinetic energy. So we have kinetic energy, which is equals to 1 by 2 mv square, the general formula, and we know the velocity equation, which is omega root r square minus y square. So this is whole square. This becomes I 1 by 2 m omega square and the root cancels, giving the r square minus y square. Now what is potential energy? If you have remembered in 11th grade, for when you did electric potential energy and gravitational potential energy, well, you always had to do some force against force which displaced the body or the particle by a small distance dx, and here the work was done in opposite. For gravitation it was in the same. Well, for here we also displace the body by a small distance. Let's just say a mass spring system like this gets displaced by a small distance dy, and here the restoring force is F. So here for potential energy, the small work done is minus force into dy. Minus signs mean that the restoring force acts on the opposite way of the displacement produced. Now we know that force is equals to mass into acceleration. Now acceleration is just minus omega square y, and we have dy. This minus becomes plus, so dw equals to m omega square y dy. Now let's integrate both sides. So we get integration of dw equals to integration of m w square y dy, and here this displacement goes from 0 to y, and this starts off with nothing, so it just starts unoscillated, and then it oscillates to a displacement of y, giving us work equals to, well, here m omega square are constant, giving us the integration of y, which is just y square by 2. So y square by 2 y to 0. So when we put y, we get y square by 2 minus, well, if we put 0 back, we get minus 0. Therefore, the potential energy is the work done, which is equals to 1 by 2, this 2 comes out, m omega square y square. Now here, as I discussed earlier, the total energy is equals to the sum of kinetic energy plus potential energy, which is 1 by 2 m omega square r square minus y square plus 1 by 2 m omega square y square. Now let's do some quick maths. Here we will just get 1 by 2 m omega square r square, which is the total energy of a body in simple harmonic motion. Now what you require for the syllabus is also the energy variation during simple harmonic motion, which you have to use by the information of kinetic energy and potential energy. So here I'll rub out the energy part. So here, for the energy distribution curve, the body will go from 0, this is the mean position, minus r, one extreme end and the other extreme end. So here, for the max kinetic energy to be max, y must be equal to 0, right? So that means that the kinetic energy is max here, and the minimum is when y equals to r. So here that means it's also minus r and r because they're same in magnitude. Now here the energy is a curve, not a straight line, because of a mathematical representation of square and that. So here it's like this, goes up and goes down like that. So this is kinetic energy. Now for potential energy, it's the opposite, because we have max potential energy when y is equals to r. So these 2 points. So let's say that the energy is going up. I forgot to mention that. So that means the max energy should be here. So that means y equals to r. That means for the potential energy it is here. And the minimum when y equals to 0. So that means it's minimum here. So it's like this, goes up. This is our potential energy and this is our kinetic energy, and this is the energy distribution curve, and that is all required for simple harmonic motion. Now I'll be covering the rest of the rotational dynamics in the future videos soon. Thank you.